For over a century, the electrical grid relied on sheer physical mass. Massive spinning steel rotors inside thermal power plants carried immense kinetic energy. If the grid's frequency wavered, that physical momentum naturally resisted the change, acting as a structural shock absorber. Today, that mechanical mass is disappearing. As solar, wind, and battery storage replace coal and gas, physical momentum is being replaced with a solid-state architecture driven entirely by software and power electronics. This graphic shows the structural breakdown. On the left, legacy thermal generation, heavy iron. On the right, the new configuration, digital signal processing cores. If an asset doesn't directly turn a physical rotor to interface with the grid, it's an inverter-based resource, or IBR. Utility-scale solar, wind turbines, and battery energy storage systems all fall into this category. Their connection to the wider power network relies entirely on software algorithms, translating their energy into grid-compatible AC power. To understand how a 100% renewable network actually functions, we have to look inside these systems. We need to deconstruct IBR internal architecture, map the new physics of failure, and analyze the grid-forming firmware required to prevent systemic collapse. The technical hurdle for a zero-carbon power system has evolved from mechanical engineering into a high-frequency data transmission problem. When evaluating renewable assets, there is a persistent assumption that the visible physical components, like the sweeping blades of a wind turbine, directly dictate how the machine interacts with the electrical grid. This diagram shows the internal mechanics of a modern Type 4 wind turbine. Notice the firewall. The physical rotor and generator are completely decoupled from the grid. 100% of generated power flows strictly through the electronic power converter. Older Type 3 models, known as doubly fed induction generators, operate differently. Their stator connects directly to the grid, making them only partial IBRs. Because they lack a total electronic firewall, they are highly sensitive to grid faults. They require precise low-voltage ride-through software tuning and physical crowbar circuits to survive sudden voltage drops without destroying the machine. While wind retains a spinning physical component, solar and battery storage systems are pure silicon. They possess absolute zero physical inertia. In a modern hybrid plant, the operational flow is entirely electronic. DC current from solar arrays flows into the battery energy storage system. The power conversion system acts as the brain, executing complex logic to convert it into grid-ready AC power. Whether the original energy comes from capturing the powered sunlight, harvesting the force of wind, or discharging localized chemical batteries, the wider grid never sees those sources. It interacts exclusively with a sophisticated software machine, functioning as an electronic firewall. Because these converters act as the sole gateway to the grid, they hold immense concentrated value. In a billion-dollar renewable energy project, up to a fifth of the total capital expenditure is dedicated entirely to these highly sensitive inverter blocks. This concentration of solid-state electronics introduces unique vulnerabilities. This exploded view of an inverter cabinet illustrates what engineers call the new physics of failure. The first major threat is thermal stress. Components like high-power insulated gate bipolar transistors and DC link capacitors are repeatedly subjected to massive daily load swings and high ambient temperatures, leading to accelerated physical degradation. Next is the electrical threat. The high-frequency switching inside these inverters generates severe harmonic distortion. If left unchecked, these aberrant frequencies overheat nearby transformers and trigger protective relays, resulting in unexpected plant shutdowns, known as nuisance trips. To protect the hardware, operators install power quality analyzers to continuously monitor the grid's waveforms and detect the specific frequencies of the distortion. Once identified, physical filters are deployed to block these high-frequency currents or provide a safe, low-impedance path to shunt them harmlessly to ground. Yet the most insidious vulnerability isn't physical at all. It resides in the programming. Because an inverter responds to grid faults using synthetic firmware rather than physical momentum, those programmed responses can shift over time. Essential algorithms dictating low-voltage ride-through and high-voltage ride-through protocols can suffer from parameter drift, pushing the asset out of alignment with strict regulatory standards. To prevent this grid code compliance drift, Operators must constantly push mandatory cyber patches and firmware updates, recalibrating the internal algorithms so the asset reacts exactly as expected during a true system emergency. Securing a solid-state energy network requires a continuous cycle of active firmware management and precise harmonic mitigation. To maintain stability across thousands of miles of transmission lines, an inverter-based resource has to perfectly emulate the exact electromagnetic properties that legacy synchronous machines used to provide naturally. That emulation requires two distinct outputs. First is active power. This represents the actual energy transfer that drives physical work, like running industrial motors or lighting a city. Injecting active power provides virtual inertia and rapid frequency containment, arresting rapid drops in the grid's operating frequency. Second is reactive power. This is energy that continuously oscillates between electromagnetic and electrostatic fields without actually being consumed. Its strict purpose is to sustain localized voltage profiles. Without a sufficient baseline of reactive power to support the voltage, active power cannot physically travel across the transmission lines. During a transient grid fault, system voltages plunge. Inverters must immediately inject dynamic reactive current to recover the voltage curve. If the localized demand for reactive power exceeds the supply, it triggers a runaway effect, resulting in a sudden, catastrophic regional blackout. Because these outputs are entirely synthetic, utility regulators have established a 100 standard. This chart shows the specific obligations enforced by IEEE 2800. Utility-scale solar and battery systems are legally required to actively control voltage profiles, endure dynamic ride-through scenarios without tripping offline, and provide immediate grid fault current support. Digital programming now dictates the stability circuits once provided by spinning rotors. As legacy plants retire, modern networks approach a critical bottleneck, the 40% penetration threshold. Once inverter-based resources make up more than 40% of the total grid mix, standard operational technology begins to fail. Currently, the vast majority of installed systems use grid-following inverters. These function strictly as controlled current sources. They require a phase-locked loop to measure an existing external voltage waveform. The inverter essentially listens to the grid and then injects a matching current to synchronize with it. The flaw in this design appears in weak networks with low short-circuit ratios. When a fault occurs, the external voltage reference wavers. Without a strong signal to follow, the grid-following inverter's control loop becomes highly unstable, often causing the unit to trip offline exactly when the grid needs support the most. Overcoming this limitation requires the implementation of grid-forming inverters. Unlike their predecessors, these act as controlled voltage sources. They do not wait for an external signal. By utilizing precise internal clock references, grid-forming inverters independently generate their own voltage amplitude, frequency, and phase angle. They establish a rigid electrical foundation that natively stabilizes ultra-weak networks. This image highlights the speed of this digital emulation, which outpaces the mechanical hardware it replaces. Look at this data point for phase angle response. By immediately calculating the deviation, a grid-forming inverter adjusts its output voltage phase angle and injects dynamic active and reactive power in under 2 milliseconds. This stabilizes the grid before mechanical protection relays even register that a fault has occurred. Upgrading to grid-forming firmware is not an optional enhancement. It is the uncompromising baseline required to keep an entirely solid-state grid synchronized. The era of heavy iron stabilizing our electrical networks is definitively over. To maintain resilience in this new configuration, operators must execute 3 distinct strategies simultaneously. First, active digital firmware management. Without strict adherence to mandatory cyber patches and parameter recalibration, grid code compliance drift will render these assets useless during a crisis. Second, physical hazard mitigation. High-frequency electronics generate destructive harmonic distortion, requiring sophisticated power quality diagnostics and physical filters to prevent critical thermal failures. Finally, the widespread integration of grid-forming software. By coupling this capability directly with utility-scale battery energy storage, the network gains the immediate synthetic inertia it needs to survive severe faults. While the exact mechanical thresholds of legacy relays are increasingly abstracted, the operational limits of software logic and solid-state converters dictate the survival of the wider network. The successful operation of a 100% renewable grid depends on the precise, real-time execution of synthetic grid physics.